Most students are joining. We have around 35 participants now, and more people are joining. We are contacting them in the group, so they'll be joining. We can start the session. Good evening, students. Today, the topic of discussion is simulating drones with MATLAB and Simulink for aerothon competition. And the resource person for the day is Mr. Veer Alakshendra, who's a senior team lead of MathWorks. He's a mechanical engineer with PhD in dynamics and control. And we also have Mr. Kushin Lakra, who's a aerospace engineer in various aerospace competitions across the world. And with this, I invite Mr. Veer and Kushin to take part.
Thanks a lot, Vijay, for the introduction. Hello, everyone. Good evening. Welcome to the webinar on simulating drones with MATLAB and Simulink for SAE India AeroTHON competition. So before we start the webinar, I would like you to show a video, and probably then we'll start the webinar. So this is a video we have created from the simulation. Here you'll see that our drone is taking off, and we do have the multiple views here. So the drone is taking off, and it will be moving through some navigation points, and finally it would be landing to the its landing point, target point, where it is supposed to drop its payload. And that's where it is reaching the target point. And here it drops the payload and goes back to its target. If you think that, is it something similar you wanted to do for your competition SAE AeroTHON, then yes, this webinar is for you. Welcome to the webinar. As the Vijay introduced, myself Kushin Lakhara, and I'm working with MathWorks as an aerospace engineer, and I especially support and mentor the student competition teams in the aerospace domain. Along with me, the Veer Alexandra is there, my colleague who is the senior team lead and mentor the automotive competitions worldwide. Hey Veer, would you like to say hi to our audience?
Hey, hi everyone. I hope you all are excited. You just saw some exciting simulation result that we have got, and I suppose is very much relevant to you guys as well. So we'll kick off the presentation now. So Kushin will go through some of the topics, and after that, I'll come back for a short session. So yeah, thanks, Kushin.
Thanks, Veer. So today we are going to learn about model-based design. We'll be discussing about what is it and why is it important and how does it help us. Moving forward, we will be discussing about 6 degree of freedom modeling, and we'll be having the technical demos where we'll be doing an aircraft simulation. So here we would be having a fixed wing aircraft. So we'll be doing its simulation in MATLAB and Simulink. Followed by this, we will be having a multi-body drone simulation where the Veer will be taking you through the session, and he would be showing how can you design your complete drone in the Simscape multi-body, and you can create the simulation video. And finally, we would be discussing about what as a MathWorks we got for you, especially for the SAE AeroTHON teams. So let's start our discussion with the model-based design. So if we discuss about the workflow for SAE AeroTHON, we see that we have the requirements from the organizers, and we do the research of the existing technology or of the previous year competition, how the teams solved this competition. So moving forward, the research from the research and requirements, we enter into the conceptual UAV design phase where the configuration is selected. It should be a quadcopter, hexacopter, octacopter, or something else. Then component sizing is performed, various components are selected. So you select which motor you should use, which propeller you should be using, what should be a battery, what should be the hardware. The material is selected. Then you would be performing the multiple analysis. It may be a structural analysis, aerodynamic analysis using CFD or FEM. And finally, you select your mechanism and performance analysis. And once you are satisfied with the design that, okay, this is my conceptual design we would be going, you go for the manufacturing. So once the UAV is manufactured, it's good to go for the manual flight testing. So we can do the manual flight testing here. But SAE AeroTHON demands an autonomous flight as well. And here we go for an autonomous algorithm development. So the autonomous algorithm development comprise of the development of guidance, navigation and control, target acquisition, perception and intelligence, and finally developing flight controller algorithm. This flight controller algorithm would be integrated on some hardware. This hardware can be your PX4 autopilot or some other one. And once this integration is done, we go for autonomous flight test. So this is the workflow which is used for the SAE aerothon competition. If we try to understand this workflow in a better way and we try to compare it with what what the workflow is used in industry generally. So we come with something similar where instead of conceptual UA design, we do have a design phase where the various components are selected, your algorithm is selected and developed. And once the design phase is done, they go for the implementation where in a particular language, programming language, or a particular programming environment, a code is developed and finally integrated on the hardware. So this is the general workflow used in the industry. So what do you think? Is it a good workflow or does it have any issues? Can you let us know in the chat? And if you feel there are problems, what do you think? What can be the problems? Uh, just a small information while putting it in chat, please please select to everyone so that we can see your messages. Or do you think that this traditional design workflow is super? We don't need anything else. This is the workflow we go for, and that's how we'll be going. And if there is something, we'll innovate in them. Any thoughts on this? Target detection. Okay, so target detection may be an issue. So from SAE Aerothon perspective, it is one of the thing we need to do. We have to detect the target, and accordingly, we have to deploy our payload. It's a one of the part we have to do. Any other problems do you feel with the traditional design workflow? Okay, let me tell you what are the problems with this. So with the traditional design workflow, first problem comes with the requirements. So here the organizers are giving you the requirements, but tomorrow when you would be moving to the industry and you would be seeing that you are getting the requirements for a particular product either from a customer or from a product design team, and sometimes those requirements are difficult to interpret, that how those requirements will lead to which algorithm selection or which component selection or design selection. Sometimes it gets difficult, and if the requirements are continuously changing from customer or from our design team, then it becomes cumbersome. Every time design requirements are changing and we are not able to understand how it would be impacting our final design. So this is the first issue we face. Moving forward, when we are in design phase, we have the components, and if we are developing the physical prototypes in this stage, obviously all the components, either it is mechanical, electrical components, everything costs us, and that makes our design process expensive. And as we are using multiple times the components, it will get more expensive, which actually prevents us for the rapid iteration. So there is less scope of the experimentation. And as we are still working on the component level, there are no system level testing is done on this stage. Once we move forward from the from the design phase, the next stage for the implementation, we need to do the coding. So mostly the manual coding is done, which is a time consuming process, and it introduces defect and variances. And as the coder's skill varies person to person, those skills may make sometimes the same code difficult to reuse. And if it is so, we face the issues with the integration. And as the integration is the final stage, if there are any issues with the design or integration, we are finding it at a very late stage. So if we find that okay, there are big issues, we need to go back to the start of the cycle and we need to fix those things. Also, we are not getting the insights that in the design process, if something was wrong, how and where it got wrong, we can't trace the issues. So this becomes the most of the issues with the traditional design workflow. So if those are the issues, what is the solution? We talked about model-based design. So can model-based design workflow helps us? So let's understand that. But first, what is the model-based design workflow? In the model-based design workflow, we are creating a digital twin and process and performing complete process over it and deciding that, okay, will it be performing as per our requirements? So let's deep dive and understand what are the benefits of the model-based design workflow. Here we can define the requirements in the model. So if the requirements are defined in the model, and later on, if we are making any changes in the requirements, we will be able to see its effect on final output or final design or our final product, which helps us in rapid prototyping. In the design, as we may need to use the multiple components. It may be the mechanical, electrical. As the model based design offers us the multi-domain design, it makes our complete design process much cheaper, because we are not here using any component in a physical form, but in a software we are using them. Once we move forward from design, we go for the implementation. In this stage, the code generation can be done. So think about, you don't need to write the code, but you are developing your algorithm, or you are developing your process, you are developing your model, and the code generation has been done from pre-existing template. As it is a template-based code and already optimized, it won't be having the errors like we get from the coders. And the final thing, the test and verification continue, as it is a software based approach. So continuously we can have test and verification. And if we found the design, any issues with the design, we can go throughout the cycle and we can correct it. This continuous test and verification allows us for the rapid prototyping. And finally, as in the during the integration stage, as we define the requirements in the model, we can actually trace what are the requirements, and which requirements are impacting our final design, and in which way. So we can see the effect of requirements on final output. So what does it help us? It helps us with the shorter timelines, because we can do the rapid prototyping, we can reduce the cost, and there is no interfacing hassles, because we are bringing everything on the same platform. So, and we are also not developing the code. So here we can focus more on engineering and less on our problems, that, okay, how once one design phase will be moving to another and how it integrate. You may feel that how the previous work that you did in another software, how it will be bringing to the next software. So all those things can be taken care in the model based design workflow. So model based design workflow is good, but how can we perform it? Can we do it using MATLAB or Simulink? So let's understand what the MATLAB is. So MATLAB is a high-level programming language and a numeric platform used by engineers and scientists to analyze data, develop algorithms, create models. MATLAB also has multiple tools which helps you for the signal and image processing, aerospace, optimization, and many more. The Simulink is the tool for the model-based design. It's a graphical environment where we do the block diagram modeling. Here we connect the blocks and signals and simulate the complete model and analyze a multi-domain system. It also offers the automatic code generation capabilities, which makes us which offers us the capability to focus on the engineering or our main design, instead of concentrating on the writing the code for particular thing and then getting the integration issues. The Simulink has a vast application, starting from the controls to aerospace. It got application in multiple fields. So as we understood that what is the model-based design and what are its benefits, let's move forward and see and learn that how can we perform this model-based design using the MATLAB and Simulink. So as the topic of today's webinar is simulating drones, so we would be here in this section developing the 6 degree of freedom modeling, which is used for the simulation. And then moving forward, we will be simulating a flight vehicle here. So before we start this session, before we start this section, I want to know if you are aware, why do we do the 6 degree of freedom modeling? Any ideas? Six degree of freedom. Yeah, pitch roll. Yes, yes, and Siraj, you are getting it right. But 6 degree of freedom is much more. XYZ, pitch your roll. XYZ. Yes, yes, we are getting closer. Accelerometer and gyro. Okay, those can be used. Any other guesses? Stability, good. We are closer. Okay, let me tell you what is the 6 degree of freedom modeling is used. Sunil says it's a 6 degree of freedom stands for 3 translational and 3 rotational motion. Yes, you are right. So the 6 degree of freedom stands for the mode. 6 degree of freedom stands for 3 translational motion and 3 rotational motion. And why do we do 6 degree of freedom modeling is to simulate any body, simulate any vehicle. So let's understand what is the 6D of modeling first, and then accordingly we will be coming back and understanding how does it help us to simulate a flight vehicle. So 6D, before we understand about the 6D of modeling, any body in the influence of the forces and moments, it develops a motion. And that's where we develop the equation. That's where the equation of motion helps us to relate this motion with the motion with the forces and moments. In case of an aircraft, there are the forces like thrust, drag, lift, and weight. So here, the lift and drag are two aerodynamic forces. Weight is a gravitational force, and thrust is a propulsion force. If we try to generalize those forces in a particular direction, consider a body reference frame where small x, y, and z are the directions from the center of gravity. So x direction is from center of gravity to the towards the nose of the aircraft, y is to from center of gravity to the right wing, and z is downwards. So those are the directions. So in those direction, if you see, the forces are capital X, capital Y, and capital Z, and moments are capital L, capital M, capital N. So those forces and moments results in the motions in the particular directions. So it results in the translational velocities, 3 translational velocities: forward velocity, sideward velocity, and vertical velocity. Those are mostly known as UVW. Then we do it, the moments results in rotational displacement and angular velocities, which are roll angle, yaw angle, and pitch angle, and roll rate, pitch rate, yaw rate. So those are the motions, and we saw the forces, but how do we connect them? How those forces and motions are related to each other? So those forces and motions are related to each other. Hello, Yash, can you mute yourself, please?
Kushin, you're on mute.
Okay.
Yeah.
Those forces and moments are related to the motion using those 6 degree of freedom motion. So we do have 3 translational acceleration equation, 3 rotational acceleration equation, and 3 angular velocity acceleration equation. So those equations helps us to mathematically model the dynamics of the aircraft and relate it to the motion. As now we understood what is the 6 degree of freedom modeling, let's move forward and simulate a flight vehicle. So for the, as we do have the aircraft dynamics from 6 degree of freedom mathematical model, what else it needs? It needs the information about the aircraft's current states. So the states include the position of the vehicle. It may be the XE, YE, ZE, attitude, obviously, which is pitch, yaw, and roll angles. Then information about the translational velocities and angular velocities. Once we do have this information, along with the information about the controls, in the case of fixed wing aircraft, the controls are the engine throttle or the controller and the control surface deflection, that is elevator, aileron, and rudders. For the case of drones or the rotorcrafts, those are the throttle of various rotors. So once we get the information about the controls and states, and we do have the 6 degree of freedom mathematical model, it actually helps us to calculate the rate of change of those states. And if we integrate those states, we get the new states. And if this is feeded back continuously, we can actually simulate the motion of complete flight vehicle throughout the time. Now, as we understood the how a simulation is performed, let's move forward and simulate the a conventional fixed wing aircraft in MATLAB and Simulink. So here we in this section we would be moving to the software tools, and here first we'll be seeing the 6 degree of freedom modeling in MATLAB, followed by we'll be doing the similar thing in the Simulink platform, and finally I will be taking you to the another demo where we'll be having the picture realistic simulation, something like this. So let's move to the tool quickly and see how do we do it. So the people who are new, let me tell you, this is the platform, no, MATLAB, and here if you see, okay, just let me close the thing so that it gets easier for all of us. So this is the MATLAB platform. As I mentioned, this is the tool used by the scientists and engineers, and it's not just a programming language, but it got much more than that. It's a computing platform. So here, this section you know as the you see is known as command window. So in command window, if you give it any command or calculation, it will be working like a calculator. For example, let me do the mass is equal to 100 kg. So I'm giving it mass, I'm giving it gravity as equal to 9.81. And now I want to calculate weight. So I will be giving it mass multiplied by G. And now I don't want to put the output in the command window. So I'll just put a semicolon and do it. I don't see. But you see this, all those variables, whatever we have typed here and called, all those variables are saved here in the workspace. So we do have a G variable here and mass and weight here. And I do have already a variable aircraft, which I was using earlier. So let me clear specifically the aircraft variable. So we can do it using clear aircraft. We can also use CLC, and everything is gone. But now if we were working in an environment and I was working on some important code and I lost this code because I closed the MATLAB, or I did something, or I forget to do it, where the code is saved. Code is not saved. So what should I do? So here we do have the script. So this is the script environment. The script looks like this, and here you can do the similar thing. So whatever you want to mention, like as we did, mass is equal to 100 and G is equal to 9.81, and then the weight is equal to say master G. I want to do that, I can do. And then finally, if I save this file, say let me save this, and let me save it in name of the weight. So I'm saving it as of weight 1. And now if you see this, once I saved the file, we do have a wait1 script here. So this file, I can call it directly in the command window by writing the wait, and you see this, I'm getting the final value. Looks like I did some calculation mistake. So pardon me for this. Uh, let me move forward and show you the more functionalities. So how the MATLAB and Simulink, MATLAB can help you. But before I show you the other capabilities of MATLAB, you may be thinking, is it's just a programming environment, but he was telling that, okay, it's not just a programming, it's other things as well. So we got an app section here as well. So there are multiple apps are there. You can choose any of the app as per your requirements. So we do have the MATLAB apps, machine learning, deep learning, some specific robotics related apps, and there are other apps also you can edit from the add-ons here. So the add-ons is the platform where the additional apps are available and additional content is available, which is freely available. You can directly use it from here. Coming back to our 6DOF modeling work. So here we saw that we had a new script. Sometimes you may need to write a long code and iterative code which need to be reused. So that's where we use the function. So how can we write a function in MATLAB? So here you see this, we do have script and function. So this function platform, this function window comes here where you can actually mention your function, that what are your input argument and name. So let me do something similar. Okay, we do have already some pre-ready functions. So I will show them how they are how they are built up and how can we use both of them. So here you see, okay, let me just minimize them. I hope the code is visible. Okay. So here the output a function is defined. Thus output arguments are this. So in my case here, the output argument are aerodynamic force and moments of the body. And I have put up the name of the function as aerodynamic. So you see this file is saved as an aerodynamics file, and I'm putting some inputs, and then whatever my code is here, I have mentioned in detail here. So that way we can do the define the MATLAB functions. Let's move forward and let me show you my favorite feature of the MATLAB, which I keep using and I love it. The reason for I love it is the it gives, I don't need the command window. So you saw this when we coded in the uh, MATLAB script. We have to call it file here, and we are seeing the file's output here. Even uh, if you run this file here, you will be seeing that the output are coming here, right? So those calculations are there, and whenever we are doing, we'll be seeing the output. But sometimes I need to go back and come and see in the command window, so I don't want to do that. So what I use the live script. Now the live script is a very interactive tool, and I love it because this gives me a flexibility to code and to add the text as well. So for example, as we were doing, the mass is equal to 100 kg and g is equal to 9.81, and then I was doing something. So I was calculating weight was mass star g. So just for example, now if I save this, so let me save it. So this is an MLX file which is saved. Now if I run this file, you see this, I'm seeing the output here only. So I don't need to go back to the command window and come command window again and see the results, and then I need to make the change code, may change the codes here. So I don't need to do all of those things. We can do everything here. So before I show you the more features of the live script, I want to show you an approach which would be we would be using to develop our 6DOF code. So here you saw this, that we are using the mass, weight, and all those variables. But think about if I do have 100 variables of aircraft, my workspace would be filled with everything. So instead of that, what we used is we used a structure form. So let me make a structure. So I am defining that aircraft.mass is equal to 100. Now I'm telling that aircraft dot weight is equal to, sorry, mass star 9.181 simply. Okay. Now if I go and see, if I go to the aircraft and I show you, the data is here in the aircraft structure. There's two are there. Now in this aircraft structure, I can create the more structure, so the data can be actually put inside, and you do not mess your complete workspace. So now let's move back to our live script and see the other features, and we'll start with the script of 6DOF modeling development. Just allow me for a second. Mhm. So let me start a new, let me restart a new script. So think about, you want to, your competition organizers want you to give them that, how was your workflow, how you did it, or you want to share it with your next year team, and you want it to make it self-explanatory. Okay, so by mistake, I opened the normal script. So in this case, we want to use the live script, and we want to give it the data, not only the programming commands, but we want to give it the text as well. So here we see that we do have the text. So I'm giving it some text here. So I am starting with my title that, okay, I do have the 6 of modeling of a fixed wing conventional aircraft, and now I'm going to do this. So let me put it as in title mode. So I went to the here and I selected a tiger and I got a good title here. Now I want to put the more data. I want to tell them that, okay, what is this file is about. I want to give the introduction. So I come up with this, but now is it just the text? Can we make it, can we use the pictures as well here? So yes, you can use the pictures. So here, if you see, you go to the insert, and here we do have the images. You can go and select the image here, but I do have a readily available image, so I can just copy paste it from there, like I work in the Word. So I just did that. Okay, did I make a mistake? Yes. Now, I want to start a next section. So let's quickly move to the building up our aircraft data. So I will be coming up from here. So in order to save the time, I have created some data in background. So you see this, that this aircraft data we have built up. So I have created aircraft.mass is equal to this. Aircraft's wing has a particular code. It has a particular area. So all those information along with the aerodynamic center, center of gravity, engine location, we have mentioned everything. Once we mentioned all those things and we want to move quickly move to the simulation. So as in the simulation section, we saw that we need to have the information about the states and controls. So let's quickly bring all of them. So here I'm mentioning the initial states that, okay, my forward velocity is 84.88, my sideward velocity is 0, my vertical velocity is 4, PQR are 0, and phi theta psi, which is yaw pitch roll, are so and so, and I'm bringing them into the initial states. Similarly, I'm mentioning the initial controls, so I'm saying the aileron, elevator, and rudder controls are so and so, and I have also given this cool throttle, so I can switch it from 0 to 100. So let me show you how can you get this cool controls. So you go to the here insert. In insert, you see the controls, and we do have the multiple controls are here. Like you have a button, you have a checkbox, drop down, edit field. So say this degree to radian, if I want to put as an edit field, so that next time when I come, I know that, okay, this is my editable field and other is not. I'll just come it here and put that edit field. Now you see the fancy edit field has come. If I do the right click here, I see the configure control auto run function, and so let's see that what is in the configure control. I can tell it that, okay, this has the data field, which is the double type. Its default value is 0. And this is going to, if I'm changing this value, this is going to run the current section. But if I want no, once I do this, the not current section, but all the section should be run. I can make the changes here and do, and also I can name it. So let me name it as delay simply. So we did this and we are good to go. So similarly we can do it for others, but just to save the time, we would be moving forward. So what we did as far, we mentioned the aircraft data, we mentioned the initial states, we mentioned the controls, what are the controls, and here we are going for we are initializing the simulation. So we are telling the controls are the initial controls only, and now it's time to set the simulation. So we are going to give it that some simulation information. So we are saying that right now the simulation time is 0, and we are going to perform the simulation or the calculation for the simulation in 0.25 seconds. So, and total time we want to run it for the 10. And I have also mentioned that it's I is equal to 1 just to initialize the for loops that we would be using uh, uh, in the simulation, and then I'm just recording the states so that we can finally record the states and we can perform the simulation. So let's start the simulation now, but before we do that, let me get you what else do we need here. So we need to write a similar while loop here. So while loop will allow us to perform the simulation from the sim till the time we don't reach the total time. So it's just performing the calculation over time. We are saying that my aircraft's current state is the record state. So the next time, whenever in the simulation, in every iteration it is coming, it would be considering the new state as a current state, and it would be performing the calculation. So it's just feeding the loop of the states as we saw in the slides, and just I'm relating the states with the current state, so that every time it knows that what is its u, v, w, p, q, r. Now there are multiple flight parameters depends on the which depends on those UVW, and those need to be calculated. So here we are calculating the airspeed, angle of attack, we are calculating the beta side slip angle, the dynamic pressure, omega vector and velocity vector. And here for this simulation, we are assuming that our gravity and density are not changing in the during the simulation, and they are constant. As we have done this, now it's time to perform the simulation. But we know that we are in simulated environment, but the aircraft has a mechanical limits. So in the controls, we can't say that, okay, you go to the 100, the controls will have the always a limit, and that's we are putting as a control saturation. So I'll give you a go through that how this control saturation is. So I'm to assess this function, what I did is, let me close this again, show you. I selected this, and I selected this function, control saturation. I click on this and I can go to the open, or I can simply press the control D, and this will open this function. So I can check that what does in this function is going. So I'm taking the control as input, and then I'm giving the output also as a control. So here I'm doing nothing but just making sure that it does not cross its maximum limit and minimum limit. So all those controls are done in this way. Here we did this, and after this it's time to calculate the forces and moments, because the forces and moments are the main factor which would be uh, affecting our motion. So here, as we saw in our slides, that there are three types of motion, forces and moments: aerodynamics, propulsion, and gravity. So here we, every time we are passing the aircraft current state and control, and accordingly we are calculating what are their effects on the aerodynamic forces, propulsion forces, and gravity forces. So here you see this, we do have the current state in the aerodynamics function. In the aerodynamics, we will be using those flight variables, so the current states need to be passed. The propulsion, similar, the propulsion function is there, gravity function is there. Once we calculate the forces and moments here, we are developing, we are just summing them up, and after the summation, we do have the total force and total moments, and then I'm doing just simple calculations. So what are we going to do is, we calls the dynamics or the Sixdorf equation. So this dynamics function is contains the equation what we saw in the slides as a Sixdorf equation. And those equations, let me show you. So here you see those long equations. We do have those three translational acceleration, three rotational acceleration, and finally those rotational velocity equations we do have. So all those dynamics has been captured here. And as we have all the forces and the moments already, those are passed to the dynamics here and the current state. And then finally, we do have the we are calculating the state rates, and the state rates are integrated, and new states are calculated. And then we are just closing the simulation with telling that, okay, the simulation time is this and that. And once this is done, we are just feeding it again for the new state. So let me bring you my original slide, which would be helpful, which would be uh, easier for us. So here you see this was the simulation block, what we performed here. Because in the simulation section, we did this. The best thing I like about it is that you can see that all the sections we made here. So you see this aircraft data, the next section is simulation, and the next section is plotting. So all those sections are separated. How do we separate the sections? So whenever you are performing something and you want to perform a section separation, you can put a section break from here, insert, and the section will be separated. Now the benefit of the section break is, whenever I want to run this file, although I do have a feature where I can run the complete script I can run, but instead of running the complete script, what I'm going to do is I'm going to run only this one. So here is a run section segment. So it will be doing the calculation for only for this. So similarly, we do have the runs aircraft data section, and then we do have a simulation section. So in the simulation sections, we are doing the simulation calculation, and here I'm doing the finally the plotting. So let's quickly see that what we got in the what we got as the output of this. So here is the first plot that we are getting as an output, and this is the second plot that we are getting. So here, this side, if you see, those are all are the controls that we have given. So we have given the aileron zero deflection, no changes, rudder zero changes, throttle for the both engines. We have given the 100% throttle, the full throttle it has. For the elevator, if you see, we have given a pulse signal. So around 5 second simulation time, it changes and it gets to a newer value. So if we see the effect of all those, how it came, so we can see in this plot. So we see that, okay, because of this change, our forward velocity started dropping. And as it was a change in elevator, around 5 seconds, we see a spike here, which take the pitch rate up. Because the pitch rate went up, our theta angle, pitch angle went up, and it also affected the vertical velocity. As we have not given any input in the aileron and rudder, we saw that there is no the phi, which is rolling angle. There are no changes. Similarly, for yawing, also there are no changes. Those are the same. So as we now understood how do we perform the 6 degree of freedom simulation of a flight vehicle and how the 6 degree of freedom is important, let's move forward and see how can we do the same thing in the Simulink, and what are the benefits of it. So just let me close this file. Okay. So here in the, if we are coming back to MATLAB environment and we are selecting Simulink. So Simulink environment is here. So once you open the Simulink environment, you are seeing that we do have the blank model, and then we do have, as per the block sets installed on the system, we get some examples as well. Those are mentioned. So here the flight simulation is there, 3 degree of freedom longitudinal frame, 6 degree of freedom airframe. So something similar what we did is here. So quickly we will move forward to the Simulink and explore what is it all about. So this is our Simulink environment. In the Simulink environment, as I told, it's a graphical modeling, a graphical approach based model based approach platform. So here we do have a library browser. So the library browser, okay, let me just take it out, which will be helpful for us. Okay. So in the library browser, if you see, there are multiple blocks are there. So all those blocks are available in the library browser. Okay. So here we see the Simulink is there, aerospace block set is there, audio toolbox is there. There are multiple toolboxes are available, lidar toolbox, robotics toolbox. So here we are going to focus on the Simulink and aerospace block set. So let me show you what all we got you in the aerospace block set. So in the aerospace block set, you got the aerodynamics related function. So if you want to calculate aerodynamic forces and moments, or you want to, if you have a digital datcom data of your drone, or your aircraft, then you can directly use this block and calculate the forces and moments. Similarly, we got the animation one. So here is the simulation 3D. So we can have a photorealistic simulation. So I'm just constraining myself from going for this, because soon we'll be coming back to this and we'll be having a photorealistic simulation. In aerospace block set, also we do have atmosphere data and all those data. So those blocks, what we saw here are very easy to use, and we can just drop and drag them here. So simply you just drop and take it here, and you see this blocks are there. Now those blocks can be easily connected to the another block. The same block, if I want to say connect same block, if I want to call, if I know the name and I want to call, I can just double click on this and I can mention that, okay, this is simulation 3D actor transform set, all those things are there, and I can calculate. So see this, I'm getting another block here now, and then if it is so, I can use it. So let us perform a simple calculation and show you, let me show you how the Simulink works. So here we, in the live script, we did have the text section, right? here we are going to this annotation form, and we are coming here, and let me write it. There is an equation that I'm going to do is I'm calculating VE. Okay, I hope it's not visible. Is it visible now? I think so, it should be. So what I'm going to do is I'm going to do the square root of u square plus v square plus w square. Okay, right? So this equation we are going to implement simply in the Simulink, and we'll go to the library browser. Okay, library browser, let me open it and back. We'll go to the Simulink blocks and commonly used blocks, and here we will be using the signal generator. So where's the signal generator? Okay, it's okay. If I don't remember, where is it? And if I know the name, I can simply come here and I can write signal generator. So I got the signal. Wow, I got the signal generator. Now what I want to do is I want to I want to make the value changes. So here I have the option of the sine wave, square, smooth, or random. All those are there. So let me take a sine wave, and I can change the amplitude or frequency. So there are for every block there are different options depending on its application. Here, if I don't understand what is the signal generator and where is it used, I can simply go to the help section. So once I click to the help section, you will be getting over to our documentation where the detailed information is there, that what is this block is about, how is it used, and what are the features. And you see this, if it has the ports, what are the ports are there, and what are the parameters. So what is the output port, waveform, time, everything is in detail is mentioned here. And this is the thing I loved most about the MATLAB and Simulink, because if I don't know anything, I don't need to ask anyone. I can just go to the help section, and my help section will help me for this. So coming back to this, we'll quickly do this. So this is signal generator. We have mentioned that, okay, this is sine wave and signal generator is there. Let me name this signal generator is, say, U, and I want to make it square wave. So we just simply got to the square wave here, and then let me do it similar for the V and W as well. So I'm just I'm trying to do the copy paste. So V, so let's change the sine wave to the square wave just to try something different. And similarly, we'll do that V2 here, which is going to be W, and let me make it a random. So I will make it a random wave, and let me put it this frequency also change. Okay, 1, fine. Now this is done. Now as per the equation, what we need to do, we need to add them. So let me take to the sum. So I just use the sum block here, and now there are two sums. So I'm adding one more sum sign here. So plus sign added, and I see the three blocks. Now those I can change it. I can change their size. Oh, it got very fatty. No worries. Can connect it here. So all those signals we are connecting. So it's easy to use. Now we have connected the signals, and we need to do the square root. So let's do it. Okay. So the final signal we would be getting from this would be, it would be what? It would be VE. Okay. Now we need to visualize this. So for this, we can go to the Simulink, and okay, let me bring my library browser here, and we can go to the sources or sinks. Let's see, we do have scope here. So we bring the scope from here, just drag and drop, it got connected. But this would be visualizing only one. So let's run it. So if I run it here, you see this, let's open this, and okay, we run this, and we saw that, okay, this result is coming. But I want to see this inputs as well. But it has a one port. So can we change the ports? Yes, we can do it. So we'll go to the layout, configuration parameters, and number of input ports. We can change it here, and then we got the multiple ports, and possibly then if I want whatever signals I want to connect. So I'm not connecting all those three signals, but just showing you them, that how we can use them. And then we connect them here, and you see this, the scope will have now the three different signals as a result. But if I want to see them in a different view, so I'll just put them into a different layout, and everything would be visible here. this was all about Simulink. We understood that how the Simulink works. So let's go back to our 6DOF model because that is the major interest to us. So just let me clean it. Let me clean this and bring a 6DOF model from here. So I do have already a 6DOF model available. Let me open this. So here I'm coming to the MATLAB command window and I'm giving a command to this that this is a command for the particular model. This will open my model here and we got our pre-prepared Simulink model. Don't worry, after this webinar we'll be sharing we will be sharing all those resources with you. So here you see this 6 degree of freedom Euler angles is there and all those we got. So here if I show you this section where the fx, fy, fz sliders are there, what they are doing, they are trying to calculate the forces, and here the below one are calculating the moments. So just let's make it simple. I selected this, I do, and I do a do a right click and I mentioned create subsystem from selection. So I got a subsystem and I make everything in a layer. Now let me name it as a forces. Similarly, I can do for the moments. Okay, okay, it's not select, was not selected. Okay, now the moments are there. So I got the moments as well. This way we can make a layer by layer, and this 6 degree of freedom Euler angle block from where we got it. So let me show you. If you go to the library browser, in the library browser, go back to the aerospace, and in the aerospace, if we go for the equation of motion, sorry, this is the equation of motion. We do have motion features of 3 degree of freedom, 6 degree of freedom, or point mass. So we are interested in 6 degree of freedom. In the 6 degree of freedom, this is the Euler angles model, which has been taken here. So I can just drop and drag here. This is the same one. So I'm just going to delete this and come back here. Now you would be thinking about in the Simulink, we are taking the blocks, but how the blocks are working? What is in those blocks? Are those blocks empty? Can we make the changes to them? So let me double click on this and you see this. Once we do this, we do have this model where we can mention the initial position. The representation is mentioned that what is my representation. I want to use the Euler angles or quaternions. The mass type is fixed, simple, variable, customer, all those there. So it's all about mentioning your initial conditions, whatever that initial mass you calculate, and then you give it. And as it is, as we discussed, the help section is there, which will always help. But I'm curious, I want to know what's inside it. So I'll just I will just right click on it and I will go open in new tab, and I see that okay, this is containing so many things here. This is containing so many blocks. So those blocks are nothing but our 6 degree of freedom equations. So here, as we do the repetitive work, sometimes we need to build everything. So just to save your work, we have already got all those blocks in the library. So you can just drop and drag and you can do this. Let me just quickly run this Simulink model and see that how the results are coming. So we see this, what the results. Okay, so the results went on my another screen. No worries. Let me bring them on the screen. So this one is here, this one is there. So we see this, okay, the results are coming as per output, and this is something similar to what we did in the MATLAB. We can do it, but some of you would be feeling, now what is that? I don't understand the graph. I want to see something photorealistic where I do see that, okay, my aircraft is flying and so and so, and I can see that, okay, this is going left or right. Can we do that? Yes, we can, and we are going to do that. So let's quickly open another model. So I do have this model already here. Let me open this model. So this is our model fly de Havilland Beaver. This is this aircraft model is there. So in the Simulink, in the previous demo, we saw this that okay, we model the equation, but now we are working on system level, and every system has a subsystem and followed by components. So how can we do that? We do this using the layer approach of the Simulink. So here, if I give you a go through of one by one, you will see this, that, okay, if we go into the pilot, this is the one where in the pilot one, there are some blocks inside, and this is doing some conditioning pilot from the pilot if joystick is connected, Simulink takes the signal from the joystick. So today we don't have the joystick, but I will show you photorealistic simulation without joystick. And this if we move to the another one, so major interest of us, the major interest is the airframe. So let's go to the airframe and see what is it. So in the airframe, we see this aircraft dynamics is there, and the parameters, like we calculated in the MATLAB program, the flight parameters, the same parameters are calculated here. So let's go to the aircraft dynamics. What is it? Does it contain 6-DOF equation? Yes, it contains a model for 6-DOF equation, and it contains another block for the total forces and moments. Let's go into the total forces and moments, and we see that, okay, aerodynamics forces, engine or propulsive forces, and gravity, everything was calculated, and finally all those forces and moments were calculated, and that's how we built the complete aircraft. Now you would be wondering, how can we if you have done already the CFD for your drone or your aircraft, how can you use that data? So here, if we go into the aerodynamics inside and we go to the datum coefficients, and we see this, that Cx alpha, Cy alpha, Cz alpha, everything is available here. So we can actually mention the Cx alpha if it is available in our workspace, MATLAB workspace. If you have imported there in the form of the tables, you can use that, or in the form of variables, you can directly call, or you can also mention it directly here. So you can click it here and base workspace open. So there are the details where you can change and make it customized. So that's how we, using the this Simulink, we can make the layers, subsystems. From components we can create subsystem, from subsystems we can create the systems. Coming back to our model here, if we saw, we do have an airframe which contains the dynamics, and we are having the pilot input, which is the controls, and the states what we discussed here are calculated inside. So we are not concerned about that. Here we are giving the input of environment. So this environment input will help us to calculate the changes in density and gravity. Here we are doing a photorealistic simulation, for which Unreal Engine is a platform which is used. And for this, we have this block. So let's open it and see that what is it inside. Okay. So this is Unreal Engine simulation. So here you would be wondering, okay, that's how do I got it? So again, all those are available in the library browser. So we go to the aerospace block set. Okay, it would be very small. So in aerospace block set, if we go, we do have the multiple things what we saw there. So we go to the animation. So animation is here. So once we go to the animation, we go to the simulation 3D. And in the simulation 3D, you will see the similar blocks. So this is simulation 3D scene configuration is there, where you can configure the scene. And then this simulation 3D aircraft is also available. If you are using rotorcraft for your drones, you can use this block, and then you can have this. Let me show you how do you set up the scene. So here we do have the default scene we are selecting. We are not developing a customized scene, but if you are developing a customized scene which is developed in Unreal Engine, then you can directly import it here and do it. We have seen a particular airport scene, we are taking it up, and we are giving it the so and so sample rate. Also, we are giving the information about the weather and the geospatial data, we are giving it here. So that's how we connect the Simulink to the Unreal Engine and photorealistic simulation. Now let's quickly move to the run it, because I'm very excited to see the what is the photorealistic simulation is. So we are running the simulation. You see this. Okay, now this is giving me error. What is the error? The operating system's joystick interface returned the status of so and so, and it's saying that we don't have the interface for the specified joystick. So actually we don't have the joystick connected. So it will throw the error. So let me go to this pilot joystick, and either I can go to the none and select it, or I am doing one thing. I'm just going to comment it. So let me comment it out, and let me bring another control. So I'm giving a constant control. So let me give a throttle 100% control. So simply I'm just connecting this one. And similarly, I'm copying this and I'm telling that, okay, I don't have any roll, pitch or yaw. So I know it won't be a straight line motion, but it would be, this will be resulting in a, uh, coordinated turn, but it's okay. We are more interested to see this, how the simulation is. So let me make it 0, and I did it. And now it's time to run this model. Okay, so this is here. Bring it. Let me bring it another window. Half window came. Okay, so this is your aircraft which is flying. Someone would be saying, I want to see it from pilot perspective or other perspective. So we do have camera angles. So let me just play with my keyboard and change your views and show you how does it how does it look. So we can actually visualize how my aircraft is performing. This is what pilot view, what I was speaking of. There are other views as well. So you can just change the variables and do this. Uh, let's save the time. We will run out of the time. I have so many things to discuss, but let me stop it here and show you the other features of the Simulink. So okay, I stopped it there. It abruptly stops. It throws an error. It's okay. Here in the Simulink, we do have multiple things. We do have the apps like the MATLAB, so you can use the apps as well. So for the iterative work, depending on the work, either it is a control system, we got the control system tuning apps, control system designer app, manager app. Then we do have the capabilities for code generation. So it doesn't matter you want to develop your code in C, C++, or Python, you can just directly do from it here. We also develop code and implement it on the hardware, and we can directly use it for the simulation purpose. For today's session, we are going to concentrate the content related to the code generation and its implementation on hardware. We will be discussing in upcoming webinar. So stay tuned for the next webinar. Here are the other feature, like the modeling. It also gives you for this one also gives you the freedom to change your parameters. So this is model setting parameter, where we can actually change that. Okay, what should be my solve? What should my solve? It should be a variable step or fixed step, or solver time. What should be the maximum, minimum? All those are customizable, like and you can do it. So Simulink is a really a vast platform, and we will not have enough time even if you give me a 1 day to discuss this. So we are going to move back to the slides, and we'll be moving forward and seeing that what all we got for you. So we saw in this section that in technical demos, we developed the 6 degree of freedom modeling equations. From there, we in MATLAB we developed them and we developed the simulation. And from them, we moved to the Simulink. We signed the simulation. Finally, we have something similar, uh, photorealistic simulation. But I know you guys are interested for the drones, quadcopter, hexacopter, or octocopters. So we got something interesting for you. So now I invite the Veer, who would be taking you to the multi-body drone simulation, and he would be showing how the video what we saw at the starting is made up of. So over to you, Veer.
Yeah, thanks, Kushin. Okay, let me share my screen so you can
Yeah,
confirm.
yeah.
Perfect. So share. Okay,
Just let me stop
share.
it.
Okay.
Yes, your screen is visible, Veer.
Visible, right? Okay, perfect. Okay. Perfect. So yeah, hi everyone. Maybe I think we are running short of time, but still, I think we have some exciting content for you guys. Now, just to give a brief that we have been showing you different tools, MATLAB, Simulink, and different applications. Now, the whole intent of doing it, what is that? Is basically that you are creating a virtual environment of a multi-domain system. So you can consider that what Kushin was talking about, that the final example, final model that you saw. So it's not only visualization that you're seeing something in 3D environment or just only the vehicle dynamics or different blocks. If you see over there that the importance is that you can do the full system level modeling. Now, all these different components, whether it is your electric source, your battery, your motors, your vehicle dynamics, where you have defined the dynamics and visualization. These are all connected. These are all coupled. So what happens is the importance of all these is that you can do multiple iterations, and based on your requirements and your design goals, you can improve or optimize your aircraft design. Now, with that motivation that why we are doing so, there's one more approach. Now, what we saw, okay, that we have equations, we convert that into a code, or we can convert that equation into a set of model using a block diagram, okay, which was Simulink, that is meant for the dynamic system, is dependent upon time. Now, another approach, there are different approaches. Like if you want to solve certain problem, you can have multiple approaches. Now, another approach which people use, that is a multi-body approach. For example, you have created something in CAD, and I'm pretty much sure that all of the teams, those who are participating in this competition, even like when I work with the automotive competition teams, that you need some kind of CAD assembly of your design. So in that case, what to do? Like if you have certain kind of CAD assembly with you for your quadcopter, can you do some kind of dynamic simulation? Yes, you can do that. So that will be a multi-body approach. So here what we are doing is, so this is one tool. I mean, just consider this as a tool. Okay. But the whole intent is that there is something that can enable you perform multi-body simulation of 3D mechanical system like your aircraft, your vehicle, your robot. These are all 3D mechanical systems. And what do we do over here? We sort of assemble bodies. Okay, either you can have a full CAD assembly, you're importing it over here in the Simscape multi-body environment, and then you can perform the whole simulation. Or if you have certain parts like STL files or step files, that also you can part by part then import it. And then you can perform the dynamic simulation. And the good part is that now since you have the CAD assemblies or you have the bodies with you, you don't need to define any equations for that. Okay. And then what all you can do with that, it's the same story which Kushin was talking about, the model-based design. But the main important thing is that you can refine requirements for mechanical for your system, for your quadcopter system. And you can discover integration issues early. For example, if you're going for selecting a motor or a battery, from here you can perform and you can see that, okay, whether your model is performing that task or not. So basically it is called component sizing and selection. So with this, what I'll do is, without wasting time, since we are running short of time, so I'll just quickly go to the demo, like how do you do that, so that you can get an understanding, because this is something new and you need to have a hold of it and a little bit understanding of the basics. So this is how the model looks like. Again, this is a system level modeling. Over here, you can have multiple components. You have full body over here of the quadcopter. Then you have different propellers. Then you have electrical components for powering up the quadcopter, and then you have an environment. We'll come back to this later. Okay. And it looks something like this when you simulate it. Okay. So you can see over here that these are
Hey, Veer, we lost you.
Kushin, can you hear me? Hello? I think I lost my internet earlier.
Yes, you were. Yeah,
Uh,
yeah.
okay,
We
okay.
lost you in a minute.
Yeah. This is some, I think some technical glitch from my side. So sorry for that.
Okay.
So let me share it again. I don't know when I stopped. One second. Share screen, share. Okay. Okay, great. Yeah. Actually, at my place, it's raining all of a sudden. So there's some kind of power technical issues happening. So yeah, sorry for that. But yeah, I was saying that. So first understand the concept of this multi-body modeling. So let's go through that. So what we'll do is we'll quickly just focus on one component. So the component that we'll focus is just the propeller. We'll see that, okay, when we are rotating it, we just want to generate that lift and create a lift and it can move upwards. That's what we want to do. So for that, what we'll do, we'll just open use SM new command. So what it does, it opens a Simulink canvas with some basic blocks which you will be needing. So in this case, I'll just remove all these unnecessary things which are not required for now. Okay. And then I'll just try to bring certain blocks which we saw just now. I'll just focus on the propeller. So what we are going to do is, if you go to the library, what is over here, this is Simscape, and this you have multi-body. Now in multi-body, you have body elements. So the goal first is to bring that STL or step file that you have created. So there was a question also that how we can bring the whole geometry. So this is the method that, for example, this is the block file solid. Okay. And then you just simply bring it over here. And I already have the propeller step file. I'll put it over here. And then from file, I'll define this inertia using custom apply, and then just press F5. Okay, so you can see that in this environment, it has come. Now, this whole multi-body, it depends upon basically one of the important thing is that frame of reference. Because why? You want to measure the motion of the vehicle when you're moving it. You need a frame of reference. So that's what, like, it is the world frame of reference, because you want to understand that, okay, if my quadcopter is flying, if it has gone 50 meters in Z direction, but from where, right? You need to have a world frame of reference. So that's what this block is doing. This is a solver configuration block. Basically, it is solving the physical signals. And this is a mechanics explorer, which is defining the gravity. Now, if I just connect it over here, so what does it mean? It means that we are connecting the propeller with the same frame of reference. That is a world frame of reference. So I'll click this, and you see over here that it is just simply just static like this. It is not moving. And if I just click on frame of reference, you can see this is a frame of reference of world frame of reference, that is fixed frame of reference. And then you have file solid frame of reference, which is again the same. So basically, both the frame of references are coinciding. There's no displacement from that or even rotation. Now, another thing is for example, if you want to add one more component at a certain distance with respect to, from this solid, that is the propeller. So what we'll do, we'll just again copy and paste the same stuff. And here, instead of this propeller, we'll just bring the cap. So we're just putting cap over here just for look purpose, nothing else, but at the same time making you understand that what we need to do if we want to displace it by certain distance. So you see over here, so this is the cap. Okay, so again what I'll do, I'll simply connect it over here, and when I connect it, let me change the color so that you can differentiate. Okay, so I'll make it red, something like this, and if I apply, okay, so you see over here it is just coinciding with the same thing. So basically, all the frame of references are at the origin, are at the world frame. So what we need to do is we need to displace it. Why? Because I want this cap to be over here on the top of it. So I'll just bring one more block. This block is rigid transform. And again, don't get scared that, okay, there are so many blocks, so you need to remember that. But the whole intent of doing this webinar is that to help you go through the different things that you can do. Okay, there are multiple learning resources which we'll be sharing with you, which can help you. And these are all self-paced tutorials. You can watch it, you can learn, you can at the same time you can model as well. So don't be scared. It is just giving an overview, an idea that how things are done and why you're doing so. So I'll bring rigid transform. So what is it? So with respect to this, how much distance along the y direction you have to displace. So in that, what you do, you double click on this, you go to translation and standard axis in positive y direction. I remember the number, it is 0.0097. I'll just put the same and simply I'll OK, and then I'll put it over here. Okay. So now once I do it, you can see that, okay, now we have learned that how we can bring some kind of custom files. Now further, what we need is we need to rotate it, right? We need to rotate it. Now let's do one thing. Let's rotate it. So what we'll do is we'll for rotating. So if you use CAD softwares, there we call it as mating. We to provide the motion with respect to between two components. So in this case, we'll go to library again and we'll go to joints. So in the joints, you can see that there are multiple joints based on the degrees of freedom you need. For example, in this case, we want to rotate it. We just require one degrees of rotational freedom. So it is revolute joint. We bring it over here, and then further in here, you can actuate it by providing some torque. So I'll just do it over here. So once I do it, so you can see over here that there's a T port over here, which is basically the input torque. So just for the sake of understanding, okay, I'll just just connect it with some constant. So let it be some 10 value. Okay. And I'll just do it. Now the problem is, if you see that it is basically, if I just isometric, okay, it is just rotating about Z axis, right? Why? Because we have not aligned it properly. So now what we'll do? Now this time again, we'll bring a rigid transform. Okay. And this rigid transform, what it is going to do is it is going to rotate the body, okay, along this axis, the perpendicular axis. So for that, what we need to do, we just need to flip it, right? If you see over here, it is X, we just need to flip it about 90 degree about X. So rotation, standard axis, X, 90, and now here you go. Okay. So you see over here that it is working fine, right? Now, as per the aerodynamics of this propeller, what should happen? Once you're rotating it, because of the aerodynamic forces, this lift will be created and it should move upwards, right? So that should be the procedure. Okay, now how to incorporate that? Okay, now until now you understood that, okay, that this is a 3D environment which is using blocks which are having, whether it is some bodies which are building from, for example, these blocks, which you just saw. Let me simple blocks over here, like body elements that you have, okay, where you just need to define some parameters, or if you have certain parts from CAD, that also you can import. And then you also learn that this is based on different frame of references, that how much you need to translate, how much you need to rotate, and then further there are multiple joints which are giving you provision to provide motion to the body, right? This you understand. Now to incorporate that when it is rotating, it should move up. That is, the lift should be created. So that we'll be doing using few more blocks. Okay. Now how do we do that? Not this one, sorry. Okay. Now how do we do that? This is how it is. So this is the same thing that we did. Again, the same thing that we did. Okay. Now what we have done is that to calculate the thrust, we are using a block which is called aerodynamic propeller. So what this block is doing is it is taking the velocity from this revolute joint. So these are actually activated. Nowadays we are activating the sensing. So it is sensing the velocity, and then the approach velocity for the time I've just given it constant, and then we are giving it to external force. So this block, what it does is it provides external force and torque. So now what is happening, that from this revolute joint you have a block which is calculating the thrust. And now how it is done, so you can have a look into this whole help file and which equations we have used, you can explore from here. This is one method. Otherwise, if you want to get more advanced, you can also bring your CFD data over here that can be brought in a form of a lookup table, and that from there you can get the thrust, and then you can input it over here in the external force. And now this block is providing the thrust, right? Now let me simulate it. Let's see what happens. Okay, and just saw it just quickly went up. Okay, so I'll just left, and with all these modifications that we did, you see over here that now it is rotating and then it is moving up. Okay, so step by step we went through. We understood that how you bring a body, how you move it, and then how you can generate a lift using a block and making some proper connections. Okay. Now another thing is, okay, let me do one thing. Okay, I just removed the block. Okay, let's see what happens. Now you see nothing is happening. It is not moving. Okay, it is not moving upwards. It is rotating, but it is not moving upwards. The reason is that you need to provide that degrees of freedom. So that's why you saw one additional Cartesian joint, okay, which is having this much required degrees of freedom. And once I activate that, again, you see it will start moving upwards. Okay. Now with this concept, I hope you got an idea that how things are modeled in SimScape multibody. There are a lot of things. We can't cover everything now. But now if you see that how step-by-step learning can be further amplified to model a full quadcopter, which can perform, we can place operation, you say, or you can say the operation in the example in this case, like it is picking up the parcel and it is then dropping it. So you see over here, this was the huge model that we have been showing you. So it's the same thing over here. Each of these propellers are just combination of the same modeling approach. So if you go over here, you see same thing. Okay, it's the same model, same block, and additional few sensors we have added. Okay, similarly with all the other propellers as well. And then we have a body which with all those different parts. Now, one last thing which I want to focus on is that this is not only that you are giving some forces and then it is flying now. Now, since we talk about system modeling, the important thing over here is your motor and batteries, right? So if you want to measure your state of charge, or you want, if you're getting into, if you want to decide what should be the size and what should be the parameters of your motor, of our battery, okay, so that it can do the task that we want to do it as per the competition. So here what you see, you can also model a perfect based on physical modeling concept. You can have motor specifications written over here, right? And you can also include a battery. So this is a full complete system level model comprising of your battery, your motors, your different 3D mechanical systems, your load and environment. Okay. Now, if once you simulate it, apart from your what you have been visualizing since now, like since long we have been repeatedly showing it, what you can do, you can further go ahead, you can build your algorithms. Like, for example, here we are building an algorithm, path planning algorithm, where that's why the reason is that it is just tracking it from going from one point to another. Okay. So you can see over here quickly, and then going back. Okay. So you can also develop the control. And now another thing which is important is that it is not only that, okay, you built it, now you want to deploy it into hardware, that's it. No. So you want to go ahead and then you can, if you can just want to build a controller, you can generate the C++ code and then you deploy in your respective hardware. Okay. And then if you're having, if you're using other hardwares like Raspberry Pi or Arduino, you can also do that, but we'll be talking about that in the coming sessions. So apart from this, you can measure a lot of information out of it. You can see over here that we are logging multiple data over here: RPM, thrust, motor specification, motor parameters, and SOC as well. Okay, so if I simulate, I think it should be done. Let me see if it is opening. If you see over here that, okay, what is the state of charge basically for the whole run? So you can see it's still, we are having a good state of charge. It is just reaching around close to 95%. Okay. So with this, I'll just stop because we have like taken a lot of time. So yeah, over to you, Kishan, and yeah, thanks everyone.
Thanks, Veer. This was a really a very good demo. I just loved that. I hope the audience would have also loved it. So let's quickly go back to the slides and see what all we got for you. Let me share my screen. I hope my screen is visible.
It's visible.
Okay. So as we discussed about multiple things, that what is the model-based design, how we did the 6-stop modeling, and finally the multi-body simulations, how do we do that? Now it's time to know more that what all we got for you. So for the
Uh,
SA Aerothon teams, we do have the
Question,
multiple things.
question, just a minute. Can you replicate the window view? We
Okay,
are
sorry.
seeing two windows here.
Okay,
We were seeing the other window question. Yeah.
presenter mode. Okay.
Yeah. And question will
Yeah,
make
yeah,
it
correct.
quick because I think we have taken a lot of time. Okay. Yeah.
Yeah, sure,
Yeah.
sure, sure, sure.
Yeah.
I hope it is now it's visible.
Yeah, it's visible. Yeah.
So we got you this essay Aerothon competition web page. So if you go to this web page, you will see that there are multiple learning resources are available, and also you can apply for the complimentary software licenses. If you have not get this link, don't worry. After this webinar, you will be getting all the resources, including the links and demos, technical demos. Uh, Moving forward, we do have a MATLAB community where we do have we are on the GitHub where the multiple repositories are available and you can directly use those codes. We do have the file exchange where our student competition team contributes, and also it's open for the public. So across the globe, people are contributing it, and you may find some really good content which interests you there. We do have MATLAB answers where the people where you can come and ask us for answers. We do have a robotics arena Facebook group, which is especially dedicated to dedicated for the student competitions. So you can come and join this group and learn that what other teams are doing. And if you have any queries that you want to discuss with other teams, probably you can do that there. We got this learning resources. So if you are new to MATLAB or Simulink and you are feeling that how can I learn more about that? So this on-ramp page is there. So if you go to this on-ramp page, you will be seeing the multiple resources we got for you here, and those resources will help you to learn the basics of those MATLAB and Simulink. So we do a MATLAB on-ramp, Simulink on-ramp, machine learning, and other on-ramps as well. So you can go through them. Uh, Moving forward, we do have also the videos. So we do have the multiple videos available for the multiple competition. So we do have the videos for the code generation, MATLAB and Simulink racing launch related videos. We got the web series for the aerospace, for robotics. So you can check them out on this web page. We do have MATLAB community. So we do have student launch. On the student launch, the technical blogs and the student blogs are available where the teams are discussing how did they, what approach they used or how did they crack the particular competition. As I mentioned earlier about the file exchange entries, so here you will find really awesome content from our student competition teams. And obviously, whenever you are asking the question, don't forget to tag us or the robotics arena or the racing launch so that our team can get you the right answers. And we got you this dedicated email ID, so you can write to us on this email ID if you have any doubt or you're looking for mentorship or you do have any technical doubt where our team can help you with. So you can write to us on this mail ID. This content we are getting for the upcoming webinars. So we will be having the webinars on how can you develop the flight controller and how can you develop the algorithm for autonomous control. And we will be having another webinar on the code generation and ground control. Just to recap, we learned about the multiple tools. We learned about MATLAB and Simulink. So when you should be used, when you have the system equations already known, or you have a calculator to solve, you need a calculator to solve, you can use MATLAB Simulink. If you want to model, simulate, and analyze, or for guidance navigation, you can use aerospace block set. Then we do have Simscape multibody and Simscape. So if you are working with the multi-domain system and you need to bring your CAD system together and want to see its real performance, then you should use those blocks. Just to recap, all those are the demos. Don't worry about them. We'll be sharing them after this webinar with you. So now we are open to questions.
Question. There were a few questions. I think most
Yeah.
of them we answered. So,
Okay.
okay. And there's one question in the starting. So, question was like how we can write this code by ourselves when you're showing the MATLAB script.
Okay.
I think, so Harsh, the thing is that we already had the script. We were copying and pasting in a blank one, and you can write it the script. The question shared multiple resources. You can have a go through it, okay, and you can start coding, and we'll be sharing it with you. So I mean, would be easy. Don't worry about that. Yeah, but if you have any questions, we are here around. You can. Um, okay, question. There's one more question. Topic about stability analysis. You want to talk about that? Yeah.
So yeah, about the stability analysis, stay tuned for the next webinar because we are going to discuss about the stability and flight controller development there. So it's a vast topic about the stability. So I will constrain myself, but I will just request you to stay tuned for the next webinar.
Thanks. Thanks, Kushin. Thanks, Veer, for joining.
Thanks a lot,
Thanks,
Vijay.
Vijay. Thank you.
We
Thank you
Thanks,
for the
will be
everyone.
sharing
opportunity.
this recording also to the students.
Hmm.
The question from my end is, will you be sharing the PPT to the students, or it is only the recording that we can share?
Vijay will be sharing everything. We'll be sharing the link to download the models as well, and as well as the slides. So what we can do is we can send it to you, and then if you can send it to the student, that will be a great help.
Yes, I'll.
Okay, yeah.
Okay.
But I mean,
Okay.
just wanted to tell everyone,
Yeah.
those who are here, that we have the resources and we have the email also where you can reach out, and we are here to help you, help the community to help you with your aerospace competition. So feel free to reach out, and yeah, I mean, all the best for your competition.
Thank you.
Yeah.
Thanks,
Thanks a
everyone.
lot.
Thanks,
Thanks a lot.
Thanks, everyone.
Thank you. Thank you. Yeah.